Right, guys, so here comes the video for the synchronous clothing. So please watch it very carefully and then we will do the interaction after.
It is well known that when a ship is sailing in following and quartering seas, the ship's motions will be augmented and the possibility of it capsizing will be increased when compared to sailing in against or beam seas. It is therefore important to possess more detailed knowledge about these risks for safer navigation in following and quartering seas. The ship handling techniques that we are to study here are also available in the International Maritime Organization Circular Guidance to the Masters for Avoiding Dangerous Situations in Following and Quartering Seas. According to the guidance, risks in following and quartering seas may arise when a ship is sailing in the same direction and at the same speed as the problem waves. Let's take a close look at the effects of these seas upon a ship's stability. The situations that should be most carefully monitored in following and quartering seas when the ship is traveling in the same direction and at the same speed as the problem waves are the encounter wave grouping phenomena, parametric rolling, the reduction of stability, and the broaching to phenomenon. These four serial phenomena are the characteristics of encounter wave grouping phenomena. First, let's take a look at encounter wave grouping phenomena. Ocean waves are an integration of irregular waves comprising those of diverse lengths, heights, and directions. Encounter wave grouping phenomena occur when a ship is sailing in rough seas that involve irregular waves with sudden serial high waves attacking the ship regularly from aft. This means that when a ship is sailing in the same direction and at the same speed as the high wave group, the ship might be constantly hit by severe serial high waves. This is called the dangerous encounter wave grouping phenomenon. To avoid dangerous encounter wave grouping phenomena, it is essential to eliminate the speed conditions that cause such phenomena. As suggested by many experimental results, the most probable condition a ship might be caught in dangerous encounter wave grouping phenomena can be expressed by the formula shown here. A combination of encounter angles of the ship to the wave coming from the aft, the ship's speed, and the wave period. According to the IMO's ship handling guidance, a dangerous zone is defined as VT being 1.5 as the norm, with a range between 0.8 and 2.0. If your ship is in the dangerous zone as defined by a combination of the ship's speed and the encounter wave period, countermeasures are imperative. Therefore, you must remove the ship from this danger zone, allowing the waves to pass by without doing any harm and avoiding the dangerous encounter wave grouping phenomena by reducing the ship's speed or by altering course. Next, we'll take a look at parametric rolling phenomena, one of the operational parameters endangering a ship in following and quartering seas. When a ship proceeds through regular longitudinal waves, the ship rolls repeatedly, for instance, to the starboard side on the first crest and to the port side on the following trough. However, when parametric rolling occurs, a ship rolls to the starboard side on the first crest and to the port side on the following crest, which means that one rolling cycle is completed for every 2 wave cycles. Consequently, the amplitude of the ship's roll is gradually magnified. To understand this more easily, let us compare ordinary rolling and parametric rolling. When you look at these motions more closely, you will notice that the ship rolls only once for every 2 cycles of passing waves, while the ship pitches once synchronous to the cycle of passing waves. This type of rolling is magnified when the encounter wave period reaches half of the ship's natural rolling period. This means that as GM decreases, the probability of parametric rolling increases. In order to avoid parametric rolling, it is necessary to adjust the encounter wave period so that it does not coincide with 1/2 of the natural rolling period of the ship. In other words, when the ship rolls once while pitching twice, you should reduce the ship's speed as much as possible to maintain her course upon judging the ship is subject to parametric rolling. Next, we will look at the dangers resulting from a reduction in stability. While sailing in following and quartering seas, great attention has to be paid to the reduction of stability. The degree of stability is determined generally by the area of the waterplane as previously shown in the chart. For instance, if a ship rides on a crest equal in length to the ship's length at midships, stability is reduced as the water planes at her bow and stern decrease due to the lower water lines at both ends. On the other hand, when a trough of the same wave passes the midships, stability is increased as the water planes at her bow and stern increase due to higher water lines. Even if a ship is in a situation with reduced stability, the time span the ship might endure this will be shorter when sailing in counterseas. Conversely, the possibility of risk is increased in following and quartering seas, as the time span is greatly increased. Now let's see how to avoid the risks stemming from a reduction in stability. The diagram shows instances of the model ship capsizing in tank experiments. You can see capsizing occurred around 1.5 when dangerous encounter wave grouping phenomena are more frequent. To avoid the risk of capsizing due to a reduction of stability, you need to have your ship sail clear of this dangerous zone to minimize the chances of riding on the crests of waves for a prolonged period. For this purpose, you also need to reduce the ship's speed or alter course, or do both to change the encounter wave angle. Broaching to is also one of the dangerous phenomena which can occur when a ship is sailing in following and quartering seas. Let's take a look at this phenomenon. Broaching to is a very dangerous phenomenon, often resulting from surf riding, in which a ship loses steerage upon being accelerated at the downslope of a wave in following and quartering seas. This is an extremely dangerous phenomenon, as the ship will lose steerage and turn abruptly with great centrifugal inertia, exposing her broadside to beam seas, often resulting in instantaneous capsizing. The broaching to phenomenon is considered to be caused by this surf riding. To avoid surf riding, you should know the critical ship speed that causes this phenomenon. The critical speed that causes surf riding is considered to be 1.8 multiplied by root L. Therefore, you should reduce the ship's speed to less than 1.8 multiplied by root L. In addition, even before reaching the surf riding condition, to avoid large surgings likely to induce the broaching to condition, it's necessary to reduce the ship's speed to less than 1.4 multiplied by root L. The formulae shown here are also cited as the criteria for avoiding broaching to in the guidance adopted by the IMO. However, when a ship is sailing in shallow waters, a surf riding phenomenon can be caused even when a ship is sailing at a comparatively low speed. This should be borne in mind, in particular by seafarers operating high-speed pleasure boats and fishing vessels. To prevent encounter wave grouping phenomena, it's necessary to take care so that any combination of important factors, such as encounter wave angle, ship speed, and wave period, do not fall in the danger zone. To prevent parametric rolling, it's necessary to take care so that the encounter wave period to the ship's natural rolling period ratio does not fall to half. To prevent a reduction of stability, it's necessary to avoid the ship riding on the crest of a wave for an extended period by reducing the ship's speed or by altering course. To prevent surf riding and broaching to, it's necessary to be aware of the critical speed leading to surf riding conditions. In addition, take special precautions to prevent these phenomena when a ship is sailing in shallow waters. For seafarers operating pleasure boats, high-speed fishing vessels, small and medium-sized ships, this should be particularly borne in mind. We hope this video helps to promote safe ship operations by reminding you to observe the basic ship handling requirements and by providing you with sufficient knowledge on the dangers of sailing in following and quartering seas. When a ship navigates in head seas, its hull is subjected to severe shocks which induce violent ship motions. As well-trained and experienced navigators, we are able to respond to this by altering the ship's course and speed as required. However, to accomplish safe navigation in head seas, it's advisable to have more reliable ship handling techniques backed by theoretical knowledge as to why these phenomena are created and how to avoid the generation of these critical effects, in addition to possessing seagoing experience. A ship at the mercy of wave forces heaves, pitches, and rolls repeatedly. ship's relative position in waves and whether it's being lifted up to the top of a crest or falling into a trough. Hogging, sagging, and twisting forces generate great deflections in the entire hull structure. In addition, the ship's speed is usually decreased by wind and wave resistance. This phenomenon is particularly augmented in head seas. So, let's take a look at the ship's pitching motion in head seas. This is the motion that has the greatest influence on the safety of a ship. Ship motions are insignificant when wavelength is shorter than ship length because the effect of the wave is small. In this condition, the bottom of the bow neither rises enough to be exposed dangerously nor dips enough for the foredeck to take on water. When wavelength is longer than the ship length, a ship pitches and heaves slowly at the front and rear surface of waves corresponding to its form. When wavelength is equal to ship length, ship motions will be most intense. The heaving of the ship on a crest and the plunging of the bow into the succeeding wave will be accelerated. In such cases, changes of water level both forward and aft become particularly great in regular waves, and this causes propeller racing, shipping seas, and slamming phenomena. Whenever a ship pitches and heaves heavily at the bow, an equivalent heaving motion is generated at the stern. Due to these motions, the stern lifts out of the sea at intervals, exposing part of the propeller and causing instant increases of propeller revolutions accompanied by intense vibrations due to the abrupt reduction of propeller load. This phenomenon is called propeller racing, and it can have adverse effects not only on the propeller itself, but also on the propeller shaft and engine. Therefore, we should make the stern draft as deep as possible so that the propeller immersion will be kept at more than 20% of the diameter of the propeller when navigating in rough seas. As resistance to the hull increases, the ship sometimes plows through the water under excess engine load. This causes what is called a torque-rich effect, and may often result in engine trouble due to overheating or in great waste of fuel. In such conditions, it's essential to reduce ship speed. Shipping seas is a condition in which a mass of green sea sweeps over the decks beyond the forecastle bulwark. A ship may sometimes suffer severe damage from the impacting green seas. Deck machinery, deck cargo, and hatch covers are often damaged by the seas thus shipped, and hatch cover damage can allow the entry of water into the holds. observe the phenomena associated with a ship shipping seas using a ship model. The phenomena differ remarkably between angles of encounter of 0 and 60 degrees. The sea shipping phenomena differ remarkably between ship speeds of 9 knots and 3 knots, even if the ship is in head seas. As you have seen, shipping seas becomes more frequent when wavelength is equal to ship length in head and countering seas. We can decrease the chances of shipping seas by reducing speed or altering course. Next, let's study the phenomena associated with shipping seas when there are irregular waves. Waves usually encountered in the ocean are a complex mixture with different lengths and heights. Let's start the trial. In this case, the ship travels at a speed of 9 knots in head seas with an average wave period of 7.13 seconds and a wave height of 3.7 meters. Under these conditions, the action of the seas being shipped is violent. Let's change the angle of encounter of the ship to waves to 60 degrees, while leaving the other factors unchanged. Under this condition, rolling increases, but no seas are shipped. In summing up the results of these trials, it's clear that the frequency of seas being shipped increases in proportion to ship speed. When a ship sails at a relatively high speed in head seas, slamming may occur. Slamming can be broken down into 3 categories. Bottom slamming is caused by the interaction of a ship's bottom and the sea surface when a raised hull plunges into the sea. Bow flare slamming is caused by collision impact with the sea surface at a relatively high speed. Bow breaking wave impact is caused by breaking waves superimposed on built-up waves at the bow of a large, full-hull type ship in head seas. These forms of slamming phenomena often not only cause structural damage to bow, bottom or bow flare, but also lead to major cargo damage. As the frequency of slamming increases, there is the chance of cracks developing in the hull structure and of metal fatigue due to repeated stresses and strains, sometimes leading to a major casualty with a total collapse of the hull. Here, in a model ship trial, we study what conditions cause slamming to be generated. It appears that the frequency of slamming increases in proportion to ship speed. In addition, it's also clearly indicated that the frequency of slamming increases when forward draft is reduced. From this table, it's possible to calculate the necessary speed reduction to decrease the frequency of slamming by half. shipping seas on decks or slamming may be generated when a ship navigates at a relatively high speed in head seas. We have studied the frequencies of shipping seas and slamming on various types of ship based on the correlation between ship speed and encounter angle of the ship to waves. To avoid any critical situation, it's essential for the navigator to handle his ship by adjusting speed optimally based on correct knowledge of these environmental conditions while taking his own ship's stability and maneuverability into consideration. A navigator's primary responsibility is to operate his ship safely in harmony with natural wind and wave conditions.
Okay, woken up?
Yes.
I'm going to ask questions on that. Right, okay. So, lights on then. You're rubbing your eyes. Right, okay. Some of the aspects of what we have morning work covered in terms of hogging, shagging, longitudinal, then comes parametric rolling. Yeah. Something that you will be avoiding at sea, or something that could be used as precautionary measures if you ever encounter such things. Now, let me just
And sorry
sorry.
for my suggestion, but I didn't understand one thing. Like, it has into like a sea.
Yeah.
It's obvious that we have a huge impact on the ship hull. But if we make it 60 degrees, the water is not coming on the deck, but we have huge rolling. So I don't understand which way is better.
Yeah, okay. It does not mean that the rolling will be huge. The rolling will develop, the rolling will be there, but it will not be as huge. So, let's say if you are rolling up to 10 degrees, and by avoiding or by turning your ship, right, you increase it by another 2 degrees. Would it make a huge difference? Not really. You are rolling anyway. Even if it goes up by a couple of degrees, it doesn't really matter. It does not really matter that the rolling would go up to many folds. It will never happen that way. If had this happened, they would not allow you to do that. So it was a combination of pitching and rolling both. So in this case, the rolling actually takes over pitching. The pitching would still be there, but rolling would actually take over here.
So we can say basically rolling is better than pitching.
Oh, well, that's debatable. All I can say is rolling will be more pronounced here. The pitching will be there. See, in some cases, as we saw, just pitching itself may not be advisable. Could you tell me why? Very good. Number one, slamming. What else was happening apart from slamming? If we were just considering pitching happening, no rolling. So apart from slamming.
Stress on the hull of the hull.
Okay, can you elaborate on that? How?
Around the hull, the middle of the ship breaking.
Absolutely. And as we saw, if you're encountering or head seas, right, and the vessel rides on a crest, right, for a longer period of time, obviously you'll agree with me that ship will be undergoing hogging and sagging on continuous basis. Because at one instance she rides on the crest, second instance, what happens? When the wave path goes past, what happens in the next instance? Less, right? So it's a continuous process. You hog, you sag, and imagine what could happen to the sea structure, crack, snap, and end of story there. So it is not always advisable to just go with the head seas or countering seas. Go at an angle. What happens now? Yes, you will develop some healing, some rolling. That's fine. That's fine. In that case, it was to avoid water being shipped on deck heavily, but serving the same purpose here.
Veronica, it will increase the chance that water will come inside the ship.
Yeah, but the water was coming, but not as much. When they turned the ship, the water may come, but the amount of water coming on the ship was like nothing compared to what it was before turning the ship.
The chances we have a cargo on board the ship, we increase the chance of losing cargo
on deck.
On deck.
Okay, fine. I understand. Now this is for the master to decide as to which one he should choose. If he has vulnerable cargo on deck, that could actually, be let loose because of the wave impact, then he might choose another option. Might not choose to turn and have a pronounced rolling happening. Apart from that, when this happens, they were talking about the GM or change in GM in the seaway because of that.
Yes.
So how well did that get observed? They said, okay, at sea, whether it's following seas, I would refer to following seas rather than head seas, because following seas, the ship tends to stay more on the crest or on the trough for a prolonged time. So what implications would that have? Let's say, for example, if you had a situation where the ship is riding on two crests, one forward, one aft, and next, I don't understand how the GM they were referring to.
And the water volume will change. That will change affecting the G.
Well, we have earlier.
The base, right?
No, we have earlier discussed that G doesn't change unless.
The base.
But you told me that unless you.
B will change. B will change. Because the underwater volume will decrease in the second position.
B will change.
So
what? Okay, fine. Buoyancy will change, but then they were referring to the GM. So what does buoyancy have to do with GM?
Affect the G level.
No, I agree, but
to decrease the
no. No, B, when it moves out, let's say port or starboard side, transversely, then the lever gets generated or lever size gets changed. But here we're not talking about the rolling effect. We're not talking about the healing of the ship. We are simply looking at the vessel sitting on crest in the middle, or ships resting on two crests. That means the trough in the middle. And they refer to the GM. They said, oh, the GM keeps changing in this case. And remember what I said, that when the ship is in this condition, right, she's prone to more rolling, which will get heavier and heavier, larger and larger. And at that point, if your GM gets smaller, imagine what will happen. The ship, as it is rolling heavily. At that point, if I squash your GM, capsize, she can capsize. You agree? Yeah? My question is, why are you saying the GM? They did give you the answer for that. They did tell you why the GM would get smaller.
Because we have a distance that's called BM, the distance from center of buoyancy to make the central.
Right.
So decreasing also.
But then the BM, how can I associate that with GM? Because B and G are independent entities, right? If the B is moving, it should not affect G. As earlier discussed, G is only affected if you add discharge or shift weight?
In this case, I think it will control steering.
Not really. No. 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 Okay, in the meantime, I'm just opening up my folder. That allows you some time to think and let me know.
What should move the shift?
No, but like,
What should move the end? When the end moves.
and will be moved if the B in like just like you create the like can you understand? The shift and if it's like goes down and down like B moves like that.
Yeah, but in this case, we're not talking about problems.
Our problem is in G. So what will, we will not move recoverable. So we will
Okay.
create another BM.
Right, okay, now coming back to your theory. You told me something about BM, and I asked you how can you relate your BM with the GM? Okay? Now, I did not mean to deter you. That was my question actually to you. So coming back to your theory, what were you trying to put across when you said the BM? You said, is that what you mean by BM?
Yes.
You mean the distance from B to M?
Yes.
No?
So change because we change the position of the sensor of currency. So we will create another BM.
Okay.
And they have the relationship between the first B and B.
Right.
B
On
and
that point, on that note, right? Can I ask you to explain what? Don't tell me that this is the distance from B to M. If I ask you, okay, think of the formula. What is the formula that governs the BM?
It is GM plus GB.
Okay. Okay.
BM multiplies
Okay.
You agree?
Yes.
Q to M divided over KB and BM, right? But then BM itself has a formula on its own. Now that formula may not be applicable to a ship-shaped vessel, but you can actually refer to it as a formula for a box-shaped vessel.
GZ multiplied by displacement?
No,
No.
no. It is
The one with the sign and
no, not that one. That. Okay, that is the formula for BM, and as I said, this is valid for a box-shaped vessel to make it easy for us to understand. So if I remove this and leave you with the formula, look at the L and B, the factors here, length and breadth.
They don't change.
Now, length and breadth of what?
Underwater.
No.
So, and they are
We're talking about
what's involved.
water plane area. Okay, this is about the water plane area. Now, what is the water plane area? If you could recall and tell me what is the water plane area?
ship's longitudinal intersection point with the sea.
With the sea. Okay. So, does that mean you're talking about the area, the surface, which is in line with the water line? So, we're talking about the area of the ship that is in the same plane as that of the water surface, right? Now, what is the water surface here then? It is not still water condition. Had this been still water condition, I would have said, oh, my ship has a big water plane area that is equal to the length and breadth at the water line. This is what it is, right?
Yes.
So, what's happening here now? in the sea when the ship rides on rest.
L decrease.
L decreases, as we can see. So significantly, L was shorter, and this is only what you're left with. Same may have happened with your B, roughly. Overall effect is the reduction in this. Overall effect. So if that gets reduced, what effect or knock-on effect will have on your BM? Decrease, obviously. So, can you form the link here? If BM decreases, you know how it's going to affect your GM?
Those of the GM become smaller because there is definitely
Okay, I agree with you, but there's one link that is missing. No. I agree that BM, you told me will get smaller, and then you said, okay, as a result, the GM gets smaller when the ship is in this condition. Why do you think the GM is getting smaller? No, the GZ comes later. The GZ is governed by the GM. Because the GM is getting smaller, that's why the GZ is getting smaller. Right? But there's one link missing here. Something that I wrote a couple of minutes ago. Well, I showed you my equation.
And then
I said, you agree with this, don't you?
Yes.
So if this goes down, obviously that will go down. If that goes down,
M will come down.
M will come down. Therefore, GM will be smaller. It's not the G that's moving, it is M that's moving down. Right? So eventually, just because now the TM is getting smaller because of the BM, doesn't affect your GM. So remember, whenever your water plane area gets affected in the seaway, your GM is going to be getting affected. Okay? Even if you have actually departed with a good GM, actually things may go wrong. Things may go wrong, especially when this is happening. And I could associate that with this as well. You got a portion of press here, but you're losing the length from here. So either way, your GM is getting affected. So, right guys, can we quickly have a look at the free surface effect itself? Okay, as to how the free surface effect actually affects your stability or GM. That's the cross-section view that you're familiar with. You can see the GZ lever being formed, right? Look at the two pictures. I'm showing you one with a bigger GZ, the other with a smaller GZ. Can I keep going back and forth? What's happening here? Ship's angle of heel is not changing, right? Why do you think in this case my GZ is big and in this case the GZ is small?
The movement of the cargo.
Because the
No, I mean, no, if you can just give me a simple answer. What is the difference between the two? G, position of G, right?
in terms of height.
In this case, position of G is high, therefore small. Now, that is the same ship. We're assuming the ship contained liquid. When she was upright, the liquid was up to that level. The ship got heeled by external force. When she got heeled, the liquid moved from this side to this side. How much? We can say by that amount. See the light blue? That wedge moved from there to there. Okay. And that wedge may have some weight, some center of gravity. Center of gravity moves from there. If the weight moves, what do you think will happen to the center of gravity of the ship itself?
Move.
Okay.
50%.
No, you're actually shifting the weight within the ship.
Okay.
So
toward the shifting.
right. So I will take 2 minutes to go on a different note and then come back to this.
Okay.
My different note, I mean, there are 3 rules. with regards to shift of the center of gravity of the ship. I said when you load, when you discharge, and when you shift something with the ship. And you have answered me for the first question, the first property, which says when you load, and I gave an example of the table, remember? I said put the computer here, the center of gravity will walk towards the computer. So it follows that when you load something, the center of gravity of the ship will go towards it. When you discharge something, it will go directly away from it. But when you shift something, how would it react?
So go to then
Will follow the shift way.
way.
It will follow. That's a nice word. If that was my center of gravity of the ship, this is the deck of the ship. Okay, I'm moving something from here to here.
So move
This
with the ship.
will
The G will move with the ship.
with the ship. It'll follow. That means it'll go parallel. Okay. So if you're happy with that, if you agree, then look what's happening here. The water weight or the weight of the water move from there to there. See what's happening to the center of gravity of the ship.
Move to G1.
Move to G1. It has to go parallel. When it went to G1, while the ship is lifted, look what's happening to the GZ lever.
Yes.
Reduced. Your B won't move now because B is sitting at the center of the underwater volume already.
Yes.
But the GZ lever, which is the horizontal distance between the G and the line, got smaller just because G walked out. At the same angle, if there was no liquid in the ship, my GZ lever would have been bigger. Now, just because of the movement of liquid, my GZ lever got smaller. So, your stability got smaller. Right? My next question is, could you look at the picture and tell me? Here, I think I've rubbed it off. Remember when I wrote GM is directly proportional to GZ?
Yes.
A certain GM will give you a certain GZ lever. My GM was that big, which should give me a GZ lever of that width or that length, right? But then with the same GM, how can I have a smaller GZ lever for the same angle of field? That doesn't go well. Okay, because I know that big GM will give me that big GZ lever, but suddenly something happens and my GZ lever got short. So can I ask you to go reverse and now tell me what sort of a GM would have given me that big a GZ lever? What sort of a GM?
G1.
You will tell me a smaller GM, right?
Yes.
So can I ask you to pinpoint the location for me as to where you want that G to be sitting? Now that's imaginary, okay? My G is actually there, but I'm just imagining, oh, what sort of a G would actually give me that small G1, Z1 lever? Where would you like to place your G now?
Above the current one.
Somewhere here?
Yes.
So the best way to locate that is to do a line straight up from that G and see where it hits the center line of the ship and place your G there. Why? Because if G was there, then the lever formed would be equal to what I have it now. Does that make sense?
Yes.
So now, look at that.
GM smaller.
Got a smaller GM? So once this happens, you must use that GM, which is smaller GM, for all your stability calculations. So if I turn around and say, okay, you're departing your ship, what is your GM? You will quote me this GM and not that GM. This GM is called fluid GM. Okay. So the term fluid GM is for this GM.
Okay.
What was the term used for the previous GM? Before applying the free surface? Solid GM. Solid GM. So solid GM is the bigger one. Fluid is after applying the free surface effect. Okay. So in other words, okay, from this diagram, could you tell me what is the free surface effect? If I have to label free surface effect, which part of the diagram should I label as free surface effect? Free surface effect is measured in meter. Your GM is measured in meter. You had a previous GM which was big, then I minus the free surface effect from that, and I was left with the smaller GM.
I think
GM solid.
the distance between G and GV.
Very good. Absolutely. That is your free surface. So it follows solid GM, take away free surface effect, and you get fluid GM. I'm putting a tick mark next to my fluid GM because that is the GM that you will rely on now. That is the GM that you will put in record, and that is the GM that you base all your stability calculations on, rather than the previous GM. Okay. It will be more stringent because you have a smaller GM. That's why all your stability will come out a bit smaller, a bit lesser than original. Okay. So, any questions? No. Imagine that was one tank. Imagine several tanks producing free surface effect, and imagine the effect on the GM. That's it.
So the best way to avoid all of this story is to fill the tank with liquid and
Not to take in a look at this.
You cannot. If this was a ballast tank, I would have said fill it to full. Even the ballast tanks would actually generate free. I would have said, okay, just press it up, full tank. I can't say so. Your LNG tanks, can't say so. Your oil tanks, you have to leave some void space, some ullage on the top, right? Which you cannot avoid. So that,
use the MoS plate.
Yeah. So
MoS plate in the tank to reduce.
you mean okay?
Also makes life is.
That is something, okay, from the naval architect point of view. You can say, okay, I will make what do you call okay, longitudinal, subdivisions, right? So that the water does not travel too fast. The further water travels, the more free surface effect will happen. So fine, but then what I'm trying to say is, if you are on the ship which is already built, you got to live with it. So when you're doing your calculations, do it carefully and take all the slack tanks into account. You got to make sure, okay, take the surface area of all tanks and then work out your free surface effect. Nowadays, I said, the computer will do it. But what if it breaks down? You then have to sit and do the calculation, or the person responsible will have to sit down. And therefore, it is important for them to know, right, as to how to calculate that.
The cargo plan is coming already from the shop, from the company. They already prepare everything.
Yeah. So are they? It is still, even though it's coming from the company, it is the master who is responsible. Master can reject that. Master can accept that only after verifying that the ship is okay stability-wise. Now that's leading me to my last topic, which was the stability criteria. Remember we mentioned minimum stability criteria? So what is it that master will have to verify, or the person in charge will have to verify before the ship takes to sea? Someone did come up with a couple of things, but they were not quite sure.
IMO?
Yes, it is IMO requirement. So it is the minimum requirement, which is called minimum intact stability requirement or criteria. So this applies to all ships. If you're carrying grain, by the way, you'll have to additionally apply. So let's not talk about grain because this course is not about grain. So the GM, they say your GM should not fall below 0.15 meter. Okay? So let's say my ship is all ready to depart. I've constructed my GZ curve, and after construction, I'm verifying these 6 items. Number 1, I'm checking my GM. If it is less than that, I'm not saying that. I cannot. So it should not be less than that. What is this for?
Fluid.
Fluid.
This one.
Absolutely, fluid. Number 2, your maximum GZ value. Remember we saw GZ values fluctuating, goes up and then goes down,
Go down.
as the
According to
curve
the-
suggests. So we're talking about the max value. This should not be less than that. So you're working out everything beforehand and putting everything in record. Then it says the angle at which the max GZ occurs. So yes, it is. So we're talking about just drop a line, vertical line, measuring the angle at which this occurs, angle of yield at which it occurs. That should not be less than 30 degrees. So you're getting a big GZ lever, but at what angle? At 25 degrees. No good. Not acceptable. Four, 5, and 6 are all talking about area under the curve. Under the curve area, what is that? And what does that signify?
Your stable area
Yeah,
that your ship will be capsizing.
yeah. So this is the resultant of your stability really. This is the net or residual area that the ship has in hand. So, in other words, dynamical stability of the ship. The rule says, the criteria says, area under the curve from 0 up to 30 degrees. So, let's mark it up to 30 degrees. We're talking about area up to 30 degrees only, right? That should not be less than meter radian, 0.055 meter radian. Meter radian simply means area which is having units of square meter. When you divide that by 57.3, which is equal to 1 radian, you convert the units to radian. Area under the curve, 0 to 40, 0.09 meter radian. And finally, 30 to 40 degrees, not be 0.03 meter radian. This is just to give you an idea that every ship will have to verify this and comply with this. If any one element here is not being complied with, you cannot say that. I'm putting a star sign there, an asterisk, simply meaning that it's not always 40 degrees, it's either 40 degrees or
Degree?
no,
No, the degree that will flat.
no, something that I had spoken before the break. I said there is one angle that is reached after the deck edge immersion angle. Does anyone remember the name of that angle? Flooding angle, absolutely. So you got to compare the two. If your flooding angle is bigger than that, then you use 40 degrees. So in other words, compare the two and choose the smaller of the two to apply here. So let's say, for example, angle of fluttering, you check it's coming to 35 degrees. Then you use 35 degrees. Then your area up to 35 degrees should not be less than that. So any questions on this? Now this is only done once you have constructed your curve, right? One last thing, how do you show your GM on the curve? The curve should have a GM as well, because you're having some minimum required GM. Where do you show it? How do you show it?
Was it vertical?
Yes.
It's like it's a 10 in 10 degree. It was like a vertical.
Yeah, it is a vertical, but the vertical is constructed at 57.3. Remember 1 radian? That's the vertical there. Whatever your GM value was, you measure that on the GZ scale. Let's say it was 0.3. You measure that and put a mark here. Okay. Now taking a ruler, you just join that bit, use a different color, use that straight to your starting point. So that line will represent GM. I can label it as the GM of the ship. Yeah. Right. So, any question on that? Seems like you guys are hungry already.
No, we are trying to memorize everything.
Everything, I know.
Yeah. To be adjustable in the place.
Yeah, I understand that. It was a short time where we had to discuss so many things, but you have been a terrific audience, really. I mean, you're interacting. Otherwise, people will so much of things to absorb. You know, they. Hey.
You make it easy.
Thank you for that.
Thank you.
So, there was still one last thing that I wanted to do. I keep saying that for the minutes, last thing. It happens really. It just occurred to me, and it was one question that the criteria wise we have looked at the twisting of the ship, right?
Mm-hmm.
We know hogging and sagging, that's not an issue. Twisting of the vessel. Now, think of an LNG carrier that has round MoS tanks. No port and starboard, just single tank. Okay, extending the full breadth of the ship, and you have series of them. Do you think such ships could still get twisted at sea? Because I would understand if you have a ship that is, if you look at the plan view of the ship, right? Now, if you have tanks here and here, which are separated by, I'm looking for the bird's eye view, right? If this was a watertight subdivision, and you load something here only, and then you load something here only, and leaving rest of the tanks empty, then yes, it might get twisted. You know, this will pull her down from this side, this will pull her down from that side, get twisted. Understand? But what I'm referring to is the MoS type tanks, right? Or even membrane, it doesn't matter. What I'm saying is that you don't have port and starboard, you just have the middle covering the entire width of the ship. Could this ship be subjected to twisting or torsion?
I think yes, according to the weather, but not as much as the other ship. According to the
if you think it will happen, can you quickly explain how this will happen at sea?
as the video.
As the video. Thank you. That's what I wanted to hear. That's what I wanted to hear, and that's what I wanted to elaborate on very quickly. Your ship is going that way, right? And you are getting seas or swells hitting you from the quarter. Okay, so that means if you look at the crest, I'm not showing the following, I'm showing seas approaching you from quarter. So crests are coming this way. So when a crest comes this way, then that's the next one coming up, and that's the next one coming up. Now wait, When the ship is riding on the crest in that fashion, see what's happening, imagine what's happening underneath. This part, the crest is producing more buoyancy. This part is producing more buoyancy. This part, there is trough, therefore more weight. This part, there is trough, therefore more weight. So imagine the weight pulling her down, buoyancy pushing her up. So this will be twisted this way, and this will tend to twist this way. Yeah. So this is what quarter seas could do to your ship. So be careful with that, especially when your ship is riding in, when the crests are approaching you with an oblique angle, like that. So that's got to be avoided. Okay. So any questions, guys, before we finish? Any questions from whatever we have discussed so far? Hope the session was effective.
Yes. I have a question. I think it's a mathematical question about the 57.3, the ratio.
Right. Okay. This is equal to 1 radian, and this is the work of the naval architect that they have come up with using 1 radian, where the GM could be actually represented and shown. So as far as stability is concerned, it has no such significance apart from remembering that this is equal to 1 radian, and the GM is measured on that. Yeah. Sorry. Right. Okay. We will actually just transfer it to you. Yeah, we'll do that. Unless you want it in the paper, I think just keep it electronic. That's better. Unless you want it to be printed out for you. Much better?
Yeah, electronic one.
Electronic one, yeah. Okay. Okay, we will do something about that. So, any more questions, guys?
Thank you.
Thanks very much.
Thank you very much.